Today's discussion delves into orchestrated objective reduction, ORC-OR, a prominent theory on consciousness. Welcome to Mind Matters, your weekly dive into the cutting edge of consciousness research. Today we're tackling one of the most intriguing and controversial theories of the mind, orchestrated objective reduction, or ORC-OR. Proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, ORC-OR suggests consciousness isn't just complex neural computation, but arises from quantum processes within our brain's microtubules. For years, this theory faced skepticism, often labeled as fringe science. But hold on to your synapses, because in the last year, specifically throughout 2024 and 2025, a wave of new experimental evidence and theoretical advancements has moved ORC-OR from pure speculation to a more robust and actively debated framework. Let's unpack the latest updates that are reshaping our understanding of the quantum brain. First, a quick refresher on the core ideas. Penrose proposed objective reduction, where quantum superpositions collapse due to gravitational effects at the Planck scale, leading to non-computable moments of insight. Hameroff pinpointed microtubules, tiny protein structures within neurons, as the biological site where these quantum events are orchestrated. Critics long argued the brain was too warm, wet, and noisy for delicate quantum states to survive. However, recent findings are directly challenging that assumption. Kicking off the new era of evidence, research published in May 2024 by the Babcock team, including Philip Kurian, unveiled significant findings on superradiance in microtubules. This groundbreaking work demonstrated that these structures can support collective quantum optical states, where tryptophan molecules within tubulin synchronize to emit light much faster and more intensely than individually. And, critically, these effects persist at room temperature. This directly combats the long-standing decoherence objection, proving that microtubules are capable of maintaining quantum coherence even in the physiological environment of the brain. The discovery suggests these tryptophan networks could act as optical qubits, processing information via biophotons. Building on the biological evidence, Associate Professor Michael Wiest from Wellesley College delivered compelling experimental results, first published in eNeuro in late 2024 and further presented at the 2025 Science of Consciousness Conference. His team treated rats with epothalone B, a drug that stabilizes microtubules, then administered anesthetic gas. They found that rats treated with epothalone B took significantly longer to lose consciousness. This strongly supports a key ORC-OR prediction. Anesthetics induce unconsciousness by acting on quantum processes within microtubules rather than solely on classical synaptic receptors. Wiest argues this is some of the first direct behavioral evidence linking microtubules to the immediate state of consciousness. Further strengthening the theoretical underpinnings, a major milestone in 2025 came from Nikolaos Mavromatos, Andreas Mershon, and Dimitri Nanopoulos, who published research in the European Physical Journal PLOS. They proposed that the hollow interiors of microtubules act as high-Q quantum electrodynamics cavities. Their model suggests that interactions between tubulin dimers and ordered water molecules inside microtubules can sustain entangled states for up to a microsecond, thousands of times longer than previously thought possible in the warm brain. This extended coherence time aligns with the timescales required for neural processing and offers a refined physical framework for microtubules as quantum information processors. The implications for how we experience reality were expanded in September 2025, with Michael Wiest and Arjun Singh Puniani's paper Conscious Active Inference 2 in the Computational and Structural Biotechnology Journal. They argued that ORC-OR offers a naturally occurring solution to the problem of discrete perceptual cycles, the idea that consciousness isn't a continuous stream, but rather occurs in frames or bursts. They proposed that quantum state reductions in microtubules provide the biological mechanism for this, implementing the brain's active inference process of constantly predicting and updating its model of reality. Finally, while much of the biological orchestration now has supporting evidence, the objective reduction part, Penrose's gravity-induced collapse of the wave function, is also undergoing experimental scrutiny. Physicist Yvette Fuentes, a keynote speaker at the 2025 Barcelona conference, is at the forefront of this effort. She's using Bose-Einstein condensates, or BECs, as a tabletop testing ground for these gravitational effects. Her work, including collaborations on the Ron Folman T-cubed phase experiment, aims to provide empirical evidence that gravity indeed interacts with quantum superpositions in the way Penrose describes, potentially proving the very trigger of conscious moments. So, as we stand in early 2026, the OR theory is no longer a mere philosophical curiosity. The conversation has shifted dramatically from if quantum effects occur in the brain to how these effects are integrated into our conscious experience. From room temperature quantum superradiance to experimental links with anesthesia and sophisticated theoretical models of quantum coherence, the updates from the last year paint a picture of a theory gaining real scientific traction. While still highly controversial, these breakthroughs suggest that our brains might indeed be tapping into the fundamental quantum nature of reality to generate consciousness, challenging classical neuroscience to embrace a deeper, more mysterious universe within us.